Okay, welcome to the course Special Topics of Semiconductor Technology. I'm Chin Wang. In this course, we're going to focus on an introduction about integrated circuit IC, and we'll talk about the basic process of a IC fabrications. Those topics including what is a semiconductor and what is wafer and the manufacturing process of a wafer, and then a lot of process required to manufacturing the IC, including thermal processes, photolithographies, plasma, and ion implantation and etch, chemical vapor deposition or metallization, etc. Basically, try to give an introduction about what is semiconductor and what is the fabrication process of an IC, and also we're going to discuss some of the application of these technologies. The textbook we are using is the Introduction to Semiconductor Manufacturing Technology by Xiao Hong. Here is a list of few references that you can go ahead search out in the library. Okay, the Science and Engineering of Microelectronic Fabrication, Microchip Fabrication, and VLSI Technology, and MEMS and NEMS. Okay, System, Device, and Structure. All these references you can find it in the libraries. You are encouraged to review all these topics, okay, using every method, including search on the web. Okay, you can find a lot of resource. It is important for you to learn eagerly and show that you try to know something about semiconductors. Okay, it's not easy for if you are the first time have the chance taking the course relating semiconductor, but we try to simplify the content. Okay, make it simple and clear for you to get a basic idea, and then maybe in the future, if you have the opportunity to work in the field of semiconductor, then you may be able to discuss, communicate with your colleague about the technology of IC fabrication and those IC applications. Here is the grading policy for this course. We might have a quiz, okay, maybe homework, and that would take into account into 25%. For the midterm and final exam will be 30% each. Another 15% will be the class participation. Okay, I do expect that we have a bilateral discussion, not only the lecture given by me, and I do expect a discussion with you. Okay, maybe we'll have Q&A section, and you can participate in discussion. All right, sometime maybe I will ask you to give a presentation. Maybe I will give you a homework or paper to read, so you need to come up and give a short presentation of what you found on those papers and what you learned. So this is a grading policy. Okay, I don't expect anyone come to see me after the grade is given. Okay, so you can know how much effort you need to devote it into your final exam. You know how much point you need to get you pass. Okay, we'll first give you a introduction about the semiconductor manufacturing process, and first we'll discuss about what is IC and a little bit about history about the invention of IC. The IC chips, okay, basically has been invented at about 1950s. There's a lot of progress after that. Okay, after taking this course, you will expect to be able to use the common semiconductor terminologies. You should be able to know what is semiconductor, what is diode, transistor, maybe capacitor, and MOS. What is this chemical vapor deposition? What is photolithography? Okay, all these spatial terminologies you are expect to know and experience. Next, you will be able to describe a basic IC fabrication sequence. What is the basic process to get an IC being fabricated? And then you can briefly explain each of the processes required to fabricate the IC. Okay, and then maybe relate your job or products to semiconductor manufacturing process. Maybe you will also be able to extend it, all those technology into your expertise, into your work. Try to relate all this technology to your expertise. Okay, let's come back to the introduction about an IC, integrated circuit. The IC chip technology has been changed our life dramatically. In the 1960s, IC has virtually no role in our daily life. But since then, the IC chip has developed in a way thousands of applications you can find in our household. The IC chip has integrated a technology revolution more significantly than other innovation in human history. IC chips are the backbone of the computer industry and have spurred related technologies such as software and internet. So every product of the information age is basically came from the IC technology. IC chip increasingly control function in cars, TV, cameras, mobile phone, and heating and cooling unit, and even daily life appliances. For example, when you turn on an automobile key to an on position. Electric current flow from the battery to the spark plugs to generate arcing that ignites the fuel and start the engine. At the same time, an onboard computer monitors the temperature and the atmosphere pressure to check the condition of the major safety features and run dozens of diagnostic programs to determine the most efficient setting for the car's driving operation. In some vehicles, onboard computer can alert the driver to a coolant leak even as they change the engine operation to avoid serious engine damage. If the coolant is completely drained, the onboard computer can turn off all unessential functions to limit the thermal load on the engine, adjust the fuel-air mixture, and alternate the firing pattern of the engine to ensure a proper operation of the car. Many vehicles are now equipped with airbags that can be triggered by acceleration sensors. In a collision, the sensor immediately sends a signal to ignite the explosive that releases gas to expand the airbag rapidly to absorb the impact. Each of these IC innovations makes travel safer and more convenient. So you can see in your daily life, you can find out a lot of applications using the IC. And from this slide, you can see a brief history of the IC inventions. Okay. The first transistor. Okay, the transistor is the IC that we're going to talk about a lot in the future of this course. Okay, transistor is basically a switch on and off. It's a signal of the binary 1 and 0. So basically, you are going to build a lot of transistors, which is where the IC is being made. The first IC is being created in AT&T Bell Lab in 1947. Those scientists who creating the transistor, including the Walter Brattain, John Bardeen, and William Shockley. These three persons, you actually received the Nobel Prize in 1956. And next, the transistor being made using single crystal germanium is being invented in 1952. Germanium is the group 4 element in the periodical table. 2 years later, in the same group 4 element, silicon is used to fabricate single crystal transistor using silicon in 1954. And that is a single transistor. But the so-called integrated circuit IC means you have more than one element one device in the applications. In Texas Instruments in 1958, the first integrated circuit was invented by Jack Kelby in 1958 at Texas Instruments. And then the first IC fabrication process using the concept of the semiconductor manufacturing process was conducted in 1961 at Fairchild Camera. These are the basic history of the IC development. This photograph shows you the first transistor being made at AT&T Bell Lab in 1947 by Jack Kelby. And this is the inventor of the transistor, John Bardeen, William Shockley, and Walter Brattain. Okay, and they got the Nobel Prize because of transistor in 1956. And this is the first IC made by Jack Kelby in Texas Instruments in 1958. At Fairchild Camera, Robert Noyce creating the first silicon IC chip in 1961. Okay, from the Fairchild Camera. Now we'll discuss about a term so-called Moore's law. Okay. During the 1960s, the IC industry developed rapidly. In 1964, Gordon Moore, a co-founder of Intel Corporation, he noticed that the number of components on the computer chip will double in every 12 months, while the price stayed the same. His prediction of this trend would hold true even to nowadays. And the trend we call Moore's law. Okay. This will be used as a roadmap to predict and develop the new technology. In early stage, this is the chip 4040 and chip 8086, 82, 86, all these early stage computers. Okay, my personal computer 286. That would be in somewhere in 1989. My personal computers. Okay, and you got Pentium 1, Pentium 2, Pentium 3, and this is a transistor included in the CPU. Okay, and it shows almost a linear trend. It's called Moore's law. Okay, and so you can basically predict how many years later how many transistors will included into a single chip. Right now, the trend of the Moore's law basically hold true even right now. Okay, so this is the trend. So the Moore's law can be used as a roadmap design to see what will be the transistor or what is the technology required to build an IC in future days. Some terms you might see in the magazine or textbook, so-called SSI, LSI, VLSI, the TSI. Say very large scale integration, VLSI. Okay, for a chip, for an IC chip, it will containing 10 to the 5 to 10 to the 7 numbers of transistors into a chip. Right now, for a sophisticated chip, you can containing more than 10 to the 11 number of transistors inside a chip. To achieve that kind of integration, you need to have a very fine technology. From early stage of technology, you have feature size in micron, say 0.35, 0.25, 0.18 in 1990. Okay, and 2001, 130 nanometer technology. Okay, this is the so-called the technology or the resolution for an IC fabrication process. And right now we are talking about 5 nanometer or 3 nanometer. They are pushing the limit to about 2 nanometers. Right now we have students working intern in TSMC, the world leading company in IC fabrication, at the 3 nanometer fab. Okay, you have to push your technology to a feature size within 10 nanometer, so you can have billions of transistors inside a chip. And this is the so-called roadmap. And according to the Moore's law, you can predict when or what kind of technology you are going to push and to develop, so you can have the product be made according to your roadmap. The feature size is the target that we try to pursue as small as possible. There are several reasons for that. First reason for that is if you reduce the feature size. For example, if you have chip made by 350 nanometer size, feature size, you may end up with a dimension like this one, the yellow, the area. But if you can reduce the feature size in about half, from 0.35 to 0.18, that means you can come up with the chips size about only 1/2. Okay, initially you have 0.35 micron, so you have entire area as only one single chip. But if you can use 0.18 technology, you can come up with the size like the purple, like so. You can 1, 2, 3, 4. If you reduce the feature size in half, you basically can reduce the size of the chip in 1/4. So you end up using the same size of the wafer, you can produce about 4 times number of chips. That means you can produce more IC that can reduce your cost. So that's why we are going to pursue smaller and smaller feature size in our IC fabrication history. On the other hand, the wafer size also developed from 6-inch, 8-inch, then right now 12-inch in diameter wafer size. The larger the wafer size actually can increase your throughput of your chips, also reducing your cost. So both increase the wafer size and reduce the feature size can both reduce your cost. So this is the way technology develop directions. Back to about year 2000. At that stage, the minimum smallest transistor is made by NEC Incorporation in 1997, and the size about 14 nanometer, which is the lower gate area here. About the lower gate area here, the size of the lower gate 14 nanometer, and this is the distance where your signal going to passing through from the left to the right. So that's the signal try to passing through, the distance of the signal passing through, about 14 nanometer. Right now, that's the technology we are talking about. We're pursuing 3 nanometer or 2 nanometer in the future. Okay, so you can came down from 14 nanometer in 1997 to right now down to about 2-3 nanometers. So once we go to the smallest feature size, then what is the limit of the feature size? All the features are composed by atom. The atom atomic about 2.5 angstrom. 2.5 angstrom, that would be about 0.25 nanometer. So each one of the device has a line width. At least you compose of few atoms. So that means you can come up with a few atoms together and form a line width. So it depends on your technology. Okay, so in earlier stage of year 2001, it predict the minimum feature size will be about 10 nanometer, but actually we're pushing the limit to about 2 nanometer right now. So you can come up with the size of the features only taking about maybe 5-6 atoms, the size of the line width, that's minimum feature size. So the IC getting smaller and smaller, so you can come up with billions of transistors in an IC. And this is the 3 nanometer technology in the year 2021. Okay, this is the structure of a transistor. Okay, this is the first IC designed by Jack Kirby. Okay, you can using hand script to draw the design. But once you have billions of billions of transistors in one IC, so you no longer is going to use hand drawing. So you need to have so-called EDA system, electronic design automation system, try to help you to design and layout of an IC. And based upon the design and layout of the IC, and then you can transform all those patterns into a mask, and using the mask try to transfer the mask image, the pattern, the layout onto silicon wafer. Over here you can see this is the mask design. Several mask design. Different color mean different mask. Using all these masks, you can come up with the transistor structure like this. This we call CMOS, complementary MOS. MOS mean metal oxide semiconductor. So CMOS mean complementary metal oxide semiconductor. The structure, okay, over here, this is called CMOS structure, and using the mask here based upon your IC design and layout. As we mentioned, the different color mean different mask. So for example, the blue one is the mask here. And the green one is the mask here, mask 1 and mask 2. The green one and orange one, okay. And this is the so-called gate area, the mask for gate. That's this one for the gate. So you have different masks. 1, 2, 3, 4, 5, 6, 7, 8. You have 8 masks here. 8 masks. Each of the masks may have several applications. You need to maybe apply in different area. So to creating this CMOS, you require minimum of 8 mask to produce an IC. A mask or reticle basically is the design of the layout of the IC. Basically, the mask is you have a quartz plate substrate, quartz substrate. On top of quartz substrate is your chrome pattern, and this is chrome pattern is based upon your IC design. And to protect the mask, you have a layer of pellicle, thin pellicle on top of your chrome pattern to protect your mask. Over here you have so-called phase shift coating. This is a material used to improve your resolution during IC fabrication. and we will discuss this in detail in the future lectures. And the so-called mask and reticle both are a layout from your design. The difference between mask and reticle is if you have a mask which is matched to the size of your wafer. Okay, this is your wafer. The square one is your mask. So your mask can cover entire wafer. The pattern of the chrome, the quartz plate, and we call this as mask. But if your mask is smaller than your wafer, each time when you transfer the image to the wafer, only compose part of your wafer size, and then the mask we call reticle. Okay, both basically are the quartz plate with chrome pattern on top your quartz plate. This slide shows you the basic wafer process flow when you try to fabricate an IC. And a big block here in the center over here we call fab. Fab is the area, is the plate actually performing the IC fabrication process. To the left, you have your materials, including chemical, solutions, base, acid, gas, all those materials. You have wafer. You have mask based upon your design from your IC design firm. So all this original material goes into the fab. This is where TSMC play their role here. In the TSMC, in the fab, there's several process, hundreds of the process steps, including metallization, chemical vapor deposition, CVD. This is chemical mechanical polishing. Okay, dielectric deposition, etch, photoresist strip, implant and photoresist strip, thermal processes, diffusion, photolithographies. All these are major processes. Okay, so hundreds of steps inside the fab performing by the TSMC. Put all those design onto the wafer to finish the IC fabrication process, and then the product sent to the so-called back end. Over here we call this is front end process. This is front end process, and this is the back end. Back end process including packaging and testing. Okay, so after the IC fabricated at the fab, going through testing, packaging, final test, and a good chip, and then will be sent to the customer. And this is the so-called back-end process. Within this lecture, we are going to focus in the fab all these processes in the front end. We're going to discuss each one of the major process. Describe how you perform this and what is the sequence to creating transistors. Okay, that would be the first chapter. We'll briefly give you an introduction about IC history and IC fabrication concept. For the summary, first, by reducing the feature size, the die size will be reduced, which allow more die per wafer, so you can reduce the cost. By increasing feature size, increasing the wafer size, more chip can be made on a wafer. Both will allow IC chip manufacturer to make more profit because you're reducing the cost of fabrications. For the Moore's law, it predicts that the number of components of a chip double in every 12 to 18 months, while the price stays the same, and the Moore's law stays true nowadays. By reducing the feature size, the die size will be reduced. Sorry, this is the same as the first one. Okay. I think we are missing one slide here. Okay, anyway, this is the first chapter. We'll discuss about the basic concept of the history of the IC. In the next chapter, we are going to discuss about the concept of semiconductors. Okay. Also, we'll discuss about the fabrication concept or some of the process. After this, we have two videos to show you, to give you a review of what is semiconductor industry. First video will be the introduction to TSMC. TSMC is the world leading company in IC fabrication. That's the introduction to TSMC. The other video will be the introduction to VLSI fabrication process. Okay, and so we let you look at the video and start to establish a basic concept. What is the process? What is an IC? Okay, and then in the future we are going to discuss each of the major steps: photolithography, deposition, metallization, chemical mechanical polishing, and etch process, also including thermal process such as annealing and diffusions. All those major processes we are going to discuss in detail in the future. Okay, alright, this will be the first chapter of introduction to the IC fabrications. See you next time.